Hey guys, I wanted to make a recording to go over a few of the things I left for today. So hopefully you took a look at the Prezi I had. It says gas laws. It has gas laws videos at the end, some of the examples, but actually the first part covers the kinetic theory and the 4 types of matter: solid, liquid, gas, plasma, that you need to know about this week. And then it covers a little bit of the phase changes, 6 phase changes. We talked about those some last week. Of course, melting and freezing, evaporation, condensation, and then sublimation and deposition. And I promise when I'm back on Monday, I'll show y'all example of sublimation and deposition in class. We'll do a demo for that. So if you went through this, you saw the first part talks about solids. Make sure you know they have a definite shape and volume, something that we can measure, and it has a shape that we can describe. The molecules are tightly packed together, moving very slightly, so we say that they're vibrating in place. And then this shows you some examples from that book: Rubik's Cube, gold, a dog. This is a picture of the winner of the world's ugliest dog competition one year. And then it moves to liquids, which have a definite volume that we can measure. Like if it's in a beaker, we can measure that in milliliters. If we're talking about a pool of water, we can measure that in gallons. You can see here's a gallon of milk. Ounces, all the different units of measurements we have for liquids, we can measure that. And then it's going to take the shape of whatever its container that it is in. Solids are going to be, vibrating in place. Liquids are going to be moving a little bit faster, typically because they've had a temperature increase and those particles start moving a little faster, and those bonds between the particles start spreading out, getting ready to break apart when it moves into water vapor, which is what we have next when we're talking about our gases. No definite shape and no definite volume is the definition for gases. The molecules are moving rapidly, they're far apart, they're bouncing off of each other. Sometimes you could think of like a propane tank having a volume, but really, like if it was not contained in that tank, the gases would just be spread out everywhere. Think about like the air in a room. If you open the door or a window, that gas is just moving in and out. Okay, and then plasma is our 4th state of matter. A lot of people kind of correlate this with like hot lava. It is way hotter than that. Think more like the temperature on the sun, which is where we naturally find plasma. Also in a lightning strike is natural plasma. And then we have man-made plasma, like in a plasma ball, plasma TV, plasma welder, lots of other examples you can think of man-made plasma. But the thing with plasma is that it is so hot that it actually strips the electrons off of the atom. So you've got the protons and neutrons in the center, and then it reaches temperatures that actually strips those electrons off. And it's balanced positive and negatively charged particles there, with the electrons moving around. So as far as plasma goes, just understanding what it is, kind of the structure of it, but it's not something we have to look at on our heating and cooling curves, which are the biggest part of this part of the unit where we're talking about the states of matter. So video on plasma, hopefully you've watched that. And then the big focus here is knowing the phase changes and what happens during those phase changes. So hopefully you looked at this chart, but what I really want you to focus on is this heating and cooling curve. So I'm going to show you a different image of that. Let's see. This is the one, and I uploaded it. I want you to really know this curve forwards and backwards. If we were in class together, I would have you draw this out, and we would label each part of this. So, not what I want to do. Okay, so first, if we're looking at the heating curve, you can see down here you have time as your independent variable. Sometimes you see this as heat energy being added, or heat absorbed. So think of time as moving this way, or heat energy being added as that time goes by. Here you have your temperature. Of course, your temperature is going to be increasing as you move up in the graph. Starting at the bottom of your heating curve, you have a solid. That's what this S stands for. So think about those particles in the solid. They're tightly packed together, moving slightly, vibrating in place. And then we're going to add heat energy to it, which is going to cause an increase in temperature. Heat and temperature are not the same thing. Temperature is a measurement of that heat energy. So if we're adding heat, imagine we have a pot of water, a pot of ice on a stove, and we're going to add heat to it, and the temperature is going to increase. And so as we move up here, temperature is increasing as we add heat energy. Then we get to a point. Right here at this point is what we call the melting point. So where you're going from a solid to a liquid. This would be your freezing point. It's not labeled on this heating curve, but I would highly recommend that you draw one of these out and add these points to it. We'll look at the cooling curve in a moment where you see the freezing point. But the melting point and the freezing point happen at the same time. If you were to observe ice melting in a pot, you would see both the solid and the liquid together. Both phases would be happening, melting and freezing. You'd have both states of matter. So you can say melting is here, freezing is going back this direction from a liquid to a solid. The key thing here to point out is what is not changing at this time. So notice here, you've got heat energy being added, but you do not have a temperature change at this part. When a phase change happens, melting, freezing, evaporation, condensation, you do not have a temperature increase. It takes too much energy to break apart the bonds from a solid to a liquid, or to put the bonds back together if you're going liquid to a solid, for there to be an increase or decrease in temperature. So right at that point, when the phase change happens, there is no temperature change. Okay, if we continue to add heat energy, and we get to a point where everything's a liquid, temperature is going to start increasing here. And this is where you have a liquid. Notice we're moving up on our graph again. And we get to this point, boiling point. Again, we're going from a liquid to a gas here, gas back to a liquid this way. So we've got evaporation and condensation. Notice that there is no temperature change here. Temperature stays the same during the phase change. All right, that's the key part. Once we get through evaporation, liquid going to a gas, we get up here and we have a gas. So if we've got that pot of ice that we started on the stove and it all melted to a liquid, now it's all evaporated out into water vapor. And again, when it is just the state of matter, you're going to see your temperature increase. So if we keep adding heat energy, you get a temperature increase. And then this shows you if you went from a solid directly to a gas, you would have the phase change sublimation, like dry ice. We talked about that some last week. Okay, the KE and the PE here, you do need to pay attention to what these mean. Again, I highly recommend drawing this out. You might draw it out a few times just to make sure you got it down. So right here, the KE stands for kinetic energy. And notice kinetic energy increases during the state of matter. When there's a temperature increase, kinetic energy increases. So right here, when we have the solid state, kinetic energy is increasing. Liquid state, kinetic energy increases. Gas state, kinetic energy increases. During those states of matter, when temperature is increasing, potential energy, the PE, stays the same. So potential energy is constant, constant, and again constant. During the phase change, however, it's the opposite. So kinetic energy is constant during the phase change for melting and freezing. Again, kinetic energy constant during evaporation condensation. Potential energy is increasing during the phase change. So here PE increases and PE increases again. Make sure you know those parts of the heating curve. Be able to read the temperatures here along the graph. You'll notice in your homework packet that it has you doing that. Like, what's the boiling point? What's the melting point? How much does the temperature increase if you go from this point to this point? There's all sorts of questions you could be asked about the heating curve. It's a graph just like any other graph. Be able to read your dependent and independent variables and what's happening with both. Okay, if we look down at the cooling curve, it's the opposite. Now, don't forget, you're starting with a gas here. That's the key thing. You want to start with the gas. You're starting up here at a higher temperature, and everything is cooling off. So heat is being released as time goes by. So you're going from a gas, then we have condensation happening, then you're in a liquid, and then we have freezing, and then it is in the solid state. Notice your potential and kinetic energy here. Kinetic energy decreases, it's constant. Kinetic energy decreases, constant, and decreases, okay? And then the potential energy is the opposite. Again, go through the homework packet, answer all of the questions on these. There's quite a few pages on heating and cooling curves for you to do just to have this practice. Circle anything you have questions on so that we can go over it this week in class. There's some videos I put up on the 1B videos that cover heating and cooling curves, but make sure you know how to read this forwards and backwards and understand what's happening with both the heating and cooling curve.